A very warm welcome to all of our audience members, students, and youths joining us tonight for the webinar Introduction to Mathematical Modeling in Transportation, brought to you by Hanoi Mathematical Modeling. Once again, it is my absolute honor to be your host today and accompany you throughout this afternoon. First of all, registration for the 2026 Mathematical Modeling Competition entry is now officially open on both the Hanoi Mathematical Modeling website and fan page. So it is fair to say that transportation is a highly relatable topic. Yet, it presents plenty of unique challenges for contestants as they dive into concepts that may seem familiar, but are full of surprises. Understanding these hurdles, Hanoi Mathematical Modeling has put together this webinar to serve as your introductory guide. Following up on our previous info session on basic mathematical modeling, today's webinar will take you a step deeper into the practical applications of mathematics in transportation, and we promise to bring you, all of you students, a much clearer and more insightful perspective on this year's theme. Ladies and gentlemen, a major part of tonight's webinar success comes from our guest speaker. And right now, I am delighted to introduce a very special guest joining us tonight. Please welcome Professor Martin Treiber, head of the Chair of Econometrics and Statistics, especially in the transport sector. TU Dresden. I'm not sure if I pronounced this correctly, so forgive me if I make any pronunciation mistakes. He has more than 25 years at TU Dresden Institute for Transportation and Economics since 2000, and he is also the author of our famous book, Traffic Flow Dynamics. And he is also the developer of the intelligent driver model, widely used in traffic flow and multi-agent simulations, with more than 25,000 citations on Google Scholar for research in traffic flow modeling and simulations. Welcome, Professor Martin Treiber. It's my absolute honor to finally meet you today. Honestly, I just read the books of yours like a month ago, and I can't believe I have this opportunity to have you joining with us today.
Okay, many thanks for the kind invitation. First, do you see my screen?
Yes, we can see it clearly.
Oh, okay, yes. So as you see, first, yes, now it's here. Many thanks. So first, I want to say many thanks for the introduction, for a warm introduction. And there's a new edition of my textbook now available, stemming from 2025. So it has also pedestrian traffic, mixed traffic, bicycle traffic, and also some extended chapters on the Miedewaan model, which is also a very famous model. So now to the actual talk. So you see at the title page some strange psychedelic patterns. So what could these patterns be? In fact, they are floating car data from a freeway in Germany, and you see this red pattern going downwards. This is a stop-and-go wave, and you see also only a few % of vehicles are recorded. It's just by live navigation. If you use Google Maps or something, you will also contribute to such tracks. Here you see very clearly what happens if there's too much traffic and there's a bottleneck. You get a traffic breakdown. That means traffic goes from blue, which means free traffic, to yellow and red, which means congested traffic. And in this seminar, I will first talk about how to model this traffic situation, and then some applications. And you will see in the applications that you can also reproduce them by yourself, because these are live simulations on the internet. So let's start. So first, the difference between micro and macroscopic models. So what is a microscopic model? Microscopic model considers the smallest object that makes sense or plays a role in a given context. So if we are in physics, so I'm a physicist by education, and of course you speak of molecules, atoms, elementary particles. Or in economics, you speak of individual decision makers. Sometimes, so in traffic flow, this is usually a driver vehicle unit. So why this strange expression? Because not only the driver, but also the vehicle determines the interactions and traffic dynamics. However, sometimes it makes sense to locally aggregate the variables. For example, if you have sound waves, there's no sense to considering every single fluctuating molecules. You will just aggregate it macroscopically to determine units such as density flow or local speed variance, which essentially is the pressure in thermodynamics. And that's the distinction to a macroscopic side. Then I also want to distinguish our models from the submicroscopic sides, vehicle dynamics, where you treat such aspects as the stability control, engine control path, and brake control path. So I think it's the distinction gets more clearly with an example. So first you see a trajectories from a left over right is the time, and from the bottom to the top is the location. So the steeper the trajectory of a single vehicle, the higher the speed. That means at the beginning, at 0 seconds, and at the end, where the traffic light, this big red trajectory is red, there you have standing traffic. Afterwards, you have moving traffic. So macroscopically, you just get the local density, that is just the number of vehicles per distance in a certain small space, or also the local speed, which is just the local average of the microscopic speed. So if you are satisfied with this, just with this color-coded thing, you can use macroscopic model. If you want a single trajectories, then you need microscopic models. However, in the following, I will only consider microscopic models, because just for your applications, for your seminar, they have distinct advantages. First, they can describe heterogeneous traffic, because each moving agent can be given different attributes, different desired speed, different vehicle length. One could even mix pedestrians, cyclists, trucks, cars all together. And this would be very cumbersome to do macroscopically, because then you need partial densities and partial flows for all this. Particularly important for the simulation is the heterogeneity that can be tackled. So first, even if I have the same model, the same vehicle category, and same driving style, drivers are no machines. That means some acceleration due to not being attentive, or due to some variables omitted by the model, give different real acceleration than model acceleration. And as usual, you hide your ignorance by introducing noise terms. So this, in the simplest case, is just some acceleration noise. You can also have a next level is cars and trucks. That means where we have same vehicles category, but we have different driving styles, timid and aggressive and so on. Every agent gets its individual parameter set. Then, of course, you can also different vehicle categories, trucks, cars, and so on. And finally, you can have also different models describing fundamental different agents, such as human versus autonomous driving, cycles. And I also simulated now some Chinese and Indian traffic, where there are also tuk-tuks, motor rickshaws, and so on. That's quite interesting. So so you are from a math institute, I assume, so you are surely interested what type of traffic models there are, first from a conceptual side and then from a mathematical side. So first, conceptual side, you can have 3 levels. As usually, the operative level is the lowest level, where you just have accelerating, braking, steering. You can also have setting winkers, using the horn, and so that's all on the operative side. That means that is what a driver directly can do in when driving a car. The next level is the tactical level. For example, when lane changing in order to leaving or entering a road, and or other discrete choice tasks. So first you need, without doing anything, you need to make a decision, and depending on your decision, you have different operative tasks. And finally, the strategic or highest level is, in our case, a route choice. Of course, in transportational planning, there are even higher levels, that for example, activity choice, mode choice, and so on. But that's outside of our topic, which is traffic flow. So we need to distinguish between traffic simulation, which also means transportation planning, and traffic flow simulation, which actually means moving objects. So, and these different conceptual levels are implemented by car following models, which tackles the operative level, lane changing or integrated models, or also non-lane based traffic, covering the tactical levels, and general discrete choice models also for tactical levels. So now I want to focus on car following models, which is a basis of all. As the name implies, one considers the reaction of a follower, that is the red guy here, to the leader, which is the blue guy here. And first consider what are the most important variables the follower needs to consider. Obviously, it's the gap to the leader, that is this SI. It's the speed of a leader and the speed of a follower. That means also the relative speed. And crucially, the gap is relevant, not the distance headway. The distance headway gives a distance from the front bumpers, but obviously the gap matters, because if a gap becomes negative, you get a crash. While the distance may be positive, particularly if the gap is the leader. So gaps always denote the bumper-to-bumper difference, and both the space gaps S and the time gaps T are the real relevant input distance variables for the leader. Of course, there can be also several leaders, and if your lane changing model is also the biggest to the side, but here I will restrict for time reasons to car follower models. So basically, what a car following model does is give an acceleration functions. Remember, operative level, acceleration implies throttling or braking, while the steering is deferred to a lane changing model. And it's named car following model, but it should also describe free traffic. And that's what I consider to be a complete model. So first, free flow. There should be a realistic acceleration profile from standstill to a desired speed, and there's the existence of a desired speed, which is obviously one model parameter. Bed space is we have some acceleration parameter, desired acceleration, and some desired speed, 2 parameters for free flow. Then we have a steady state. Steady state means things can be moving, but there's no temporal change in gaps and speeds and so on. So that's different from static, which just means stopped. So steady state means moving, but no change in the relevant variables, gaps and speeds. And then, of course, if traffic is sufficiently dense, it gets from free to interacting, and you will follow your leader with a certain time gap. It's a time gap, not a certain desired distance, because the distance increases with the speed. So in German live driving lessons, we learn always keep at least the distance half the speedometer reading. Distance in meter and speedometer reading in kilometer per hour, corresponding then to a time gap of 1.8 seconds. It's rarely met. Most people use 1.2 seconds or something, but it's a order of magnitude. I don't know if you have in your country have similar driving lessons rule. I assume so. So it's a time gap which is relevant for following. Then there are the dynamic situations. For example, closing in. That means from free traffic to regular car following situation, or if suddenly there's a speed limit, you need to decelerate. And particularly when approaching a stop obstacle, such a traffic light or a standing of a jam, there should be a regular deceleration to a stop. Also another model parameter, the desired deceleration. The lower this desired deceleration, the more anticipative the model must be. So another parameter B. And finally, also emergency situations should be handled. That means, for example, a sudden cutting in of a leader, or some unexpected happens. Then the deceleration, of course, is higher than the desired deceleration up to the maximum deceleration, another model parameter. So that's and interestingly, this alone is enough to get collective phenomena such as stop-and-go waves, which I will show later in the simulation part. So now let's get more mathematical. Basically, there are two mathematical realizations of continuous car following models. The first is coupled ordinary differential equations models. That means we have the change of space is of course the speed by definition, and the change of speed is the acceleration, and the acceleration function f defines the car following a model. So we have a coupled ordinary differential equation. It's coupled because the speed is coupled to the leading speed. And also, if we change this to the change of gap is leading speed minus own speed, then also the gap is coupled to the leader. That means coupled differential equations. Of course, we cannot solve an ODE directly because no analytical solutions exists for all non-trivial cases. So we need some solution methods. And you can also think of ODE plus solution method, explicit solution method, as an iterated map model. Iterated map, as the name implies, the state at time t, it means all speeds and positions is mapped to the state at times t plus delta t. For example, just by using the ballistic update, the speed is updated in the Euler scheme, and the space is updated with the ballistic scheme using the old and the new scheme, a new speed. So what could be a plausibility criteria? This, for example, is the acceleration function of the IDM. So it depends on three variables: speed, leading speed, and gap. And for example, consider the left one, when going to higher speeds, the acceleration decrease. So green is basically free acceleration, red is strong deceleration, and violet is emergency deceleration. So when going to higher speeds, it decreases. When going to higher gap, it increases. And when going to higher relative speeds, now here's it. When going to higher relative speeds, as here below, then the deceleration decreases, which is very important, because if you approach a stopped vehicle, you need to brake much harder than following vehicle driving at the same speed at the same gap. So mathematical, you can use all formulate all plausibility criteria just by their sensitivities. So on the speed sensitivity, that means the partial derivative of acceleration function with respect to speed must be negative. And if there's also a limit, if the gap goes to infinity, tends to infinity, and you have desired speed, then regardless of the leading speed, you have an acceleration of 0, because you are cruising at your desired speed. If the gap is the same, with increasing gap, you have increasing acceleration. The reverse is for also with the leader speeds gets higher, also get a higher acceleration. And of course, there's always a limit. If you are sufficiently far away, if a leader is sufficiently far away, you have just do not consider the leader at all. Then you can also, there's a steady state relation. So if you have identical vehicles and drivers and a given gap, then there's a certain speed corresponding to this gap, which I call here the steady state speed VE as a function of gap. And that is just defined by acceleration function of VE, and the leading speed is also steady state speed is 0. So steady state means both acceleration 0, and we have homogeneous steady state. That means also leading speed is the same speed as the follower speed. So this is just an implicit relation for the steady state speed. Yes. And then you can even formulate it. I will not go into detail here. You can say that the derivative of a steady state speed with respect to the gaps can be expressed in terms of a partial derivative of the acceleration function. So this is a very nice and general formulation, which is valid for basically all car following models which are formulated continuously. So now I will come to some example for a car following model. Mainly, I will speak about the IDM. So with IDM, an intelligent driving model is force-based. Basically, it's a superposition of a free flow force that is a self-driving. So at a speed of 0, you will just have a maximum acceleration A. If you approach the desired speed, your acceleration tends to 0. And if you go near the desired speed, the acceleration drops rather strongly to 0. To this is added the repulsive force by the interaction, which is a sort of Newtonian gravitational force only repulsive instead of attractive. Basically the same as charged particles of the same charge polarity will repel each other. So it's basically proportional to the inverse of the gap squared, and it is compared to the dynamically desired gap. And this dynamically desired gap is composed of the static desired gap, which is the minimum gap, plus the gap, the safe gap. So it's just the speed times the desired time gap. And then we have some dynamical contributions, which is, I would say, the unique selling point of the IDM, this dynamical gap. And with this, so we have 5 model parameters, and we can model basically any moving object which can accelerate and decelerate and follow particles, cars on highway. Of course, decides basically distinguished by desired speeds, cars in city, trucks, cycles, even pedestrians, where we would have 5 km/h. Time gap, remarkably, is not so much different between the different objects. It's a little bit higher for the trucks. In fact, they use the driving school recommendation speed, a distance equal half the speedometer reading. The minimum gap is only for the cycles, much lower. That's the bumper-to-bumper gap if you are stand, for example, queuing in a traffic light here, or being stuck in a standstill on a highway or a freeway. Acceleration is also of the order of 1 to 2 meters per second for all objects apart from the trucks, which, if they are loaded, have a lower acceleration. And also the deceleration is remarkably the same. But of course, you can model different driving styles. So here you see an aggressive driver. So it has all the cliches in it. So wide tires, Reebok stickers, spoilers, air spoilers, then sunglasses, and even the foxtail is not missing. So this would be correspond to a high speed, a high acceleration, and also high deceleration. That means this driver only brakes at the last moment. However, the following time is very slow, and the minimum gap is also very slow. So we see this guy literally in your back mirror. You literally see the sunglasses of this guy in the back mirror. If you have an experienced responsive driver, acceleration is still high, but the deceleration is low. That means there's a lot of anticipation, and the rest is just normal. However, there's also a relaxed driver, which has low desired speed, low acceleration values, normal desired deceleration, and high time gaps and minimum gaps. And if you have an experienced defensive drivers, it's basically the same, only that A and B, A is normal and B is low. B is low means anticipative, that is also part of defensive. Basically, you can even map all the big 4 driving psychological personalities in IDM parameters. That's one of the reasons why this model is so popular, besides that it's being crash-free. And why is it being crash-free? That's a nice mathematical exercise. So first, I make the worst case. No minimum gap, no desired time gap. Furthermore, the leading speed is 0. That means approaching a solid obstacle or a red traffic light. It means when the SR just reverts to the kinematic braking distance. And also I consider only the repulsive term. That means approaching at desired speed. And then I insert this dynamical gap, which has now just the dynamical contribution. And that sounds a little bit strange. However, this v to the power 4 divided by 𝐶𝐓² can be expressed by the kinematical needed minimum deceleration squared divided by 1b. The a's cancel away. And so that means this can be formulated as the needed kinematical deceleration squared divided by b. And this expression has remarkable properties. So consider that the situation is dynamically safe. That means the needed deceleration is less than the comfortable deceleration. Then this term even results in an even lower deceleration, because this is just than the kinematic deceleration, because it's squared. So if we just rewrite it in this, so if a simulation is safe, then the IDM acceleration is even less than kinematic. However, if the situation is critical, which is just evaluated by kinetic deceleration is greater than b, then the IDM deceleration is even still greater. It breaks more. It means the situation is dynamically brought under control. And in fact, this kinematic braking deceleration is one of the safety matrix, so the risk matrix, such as the time to collision. So now let's now we simulate this. First, I have some fact sheet. Basically, I simulate here a freeway scenario with a bottleneck. We will see this in a simulation soon, and also we will see the how the simulation responds in a city scenario. Here, the traffic light turns 0, and the queue of 20 vehicles just increases and then decreases its speed to 0 in the next red traffic light. So you see there are some deficiencies. The last vehicle will not reach the full speed. There are variants which removing this, but I will not go into detail here. In fact, here's the variant, the IDM Plus. Basically has the same formulation, only it has a distinct free flow and interacting regime distinction, and then it even looks nicer. However, not spoiling the intelligent braking strategy. That means the unique selling point. As I said, we can also use the IDM for vehicle traffic. This is a driving test of vehicles done by a German university, and you see that the stop-and-go traffic, stop-and-go wave appear. 63 cyclists on this oval road, and the IDM basically reproduces the same simulation result. Then finally, I want to mention, not going into detail much, the physio-psychological models that include what if the IDM is missing. So what is the IDM missing? First of all, it has no reaction time. That means everything is taken at the actual state. However, if you include a reaction time, you have a delay differential equation, because the acceleration is a function of a delayed states, delayed by the reaction time. You can also include different reaction times for the gap and the leading speed. The actual speed has no reaction times because you basically know it instantaneously. You could also have some response thresholds or have a risk attitude. And you also can have correlated estimation errors. So humans not only react with delay, they also have estimation errors. However, they compensate for it by a temporal anticipation. That means they anticipate their reaction distance by some heuristics. And they have also a spatial anticipation. They only do not respond to the immediate leader, but also to the next nearest leaders. That's why we feel so uncomfortable when driving behind a truck or behind some not some opaque vehicle with black mirror, black windows and so. So one implementation is the Wiedemann model. I bring this model shortly because it's very relevant for some commercial traffic flow simulators, which maybe you are also using the PDV VISIM. So that's that uses the Wiedemann model, and here we have distinct driving regimes. Each region has its own acceleration function, and it looks like this. So this is basically this, we have a three-dimensional input space, speed, relative speed, approaching rate, and gap, and we take a cut of this three-dimensional space for a certain speed, and then we can have certain regimes. So free flow, that means no, not corresponding to any leader. Then state is basically following, then approaching regime, and a critical situation. And because inside the following regime, there's no response, only if the follower, so to say, bump into the other regime, it will brake. When it will bump into the free flow regime, it will accelerate. That means it will get some circles. And for we have also here is the so that's the schematic figure. The real figure for the standard Wiedemann 74 parameters in VISIM or the Wiedemann 90 parameters looks like this. However, calibrated by me is some looks a little bit different. Remember that this is the first time, so in my new book, Traffic Flow Dynamics and Simulation, second edition, I think this is the first time the Wiedemann model is presented in full detail, because up to now it was hidden in some C code in PDV VISIM. And so the acceleration function, so as I mentioned, each of the regimes has its own acceleration function. For a certain speed, free flow, it's just acceleration because the actual speed is less than the desired speed. In the following regime is basically zero, the acceleration. In the approaching regime, it's more and more deceleration. So now I'm finished with the actual PDF presentation. I will show some simulations, mainly of the IDM with some modifications, for example, the IDM Plus. So first, I hope everybody sees now this simulation screen. And you see also on the website, it's just traffic-simulation.de. It means everybody can simulate what I'm now doing on his or her own laptop or a computer, even on the smartphone. However, it's rather fiddly on the smartphone, so I would recommend laptop. So now I start the simulation. First, this is a rather unrealistic simulation. It's a closed ring road, but corresponding is experiment. So first, nothing happens. However, you see that maybe I just decrease the time lapse a little bit, that here some vehicles driving slower, which is a color coding. The yellow, the more yellow or even red, the slower vehicle. And you see that more and more a traffic jam, a traffic wave appears. So it's a dynamically unstable. So in my textbook, it's also how to derive conditions whether model is unstable. Particularly, I even so I mark one vehicle, maybe this one. I make it even slower, and I mark this vehicle maybe. So this vehicle senses that it's needs to decelerate. However, it takes some time to get the safe gap for the leader speed, and because then he even comes too close. That means it even gets slower, and that means every follower gets slower than the leader. So this basically leads to a fully developed jam. Now increase the time lapse. So the time lapse is just increases the simulation speed. It does nothing else. And now you see also what is also the title of my slide, that the stop-and-go waves travels backwards. And remarkably, the backwards traveling speed is basically a traffic constant. It's about -15 km/h. It only depends a little bit on the average length. So how to avoid it? I just make the model more responsive by increasing the acceleration parameter. Now you see how the vehicles accelerate out of the jam, and the wave gets lower and smaller. Maybe it will not dissolve at this setting, but it gets much lower. If I make the cars even more responsive, then it will resolve. And if I make them less responsive, a new traffic wave will appear. Interestingly, I can also, if I just start, if I provoke, so here you see hardly, so it seems really nothing happens. Now I click on the simulation, deceleration some vehicles, creating an initial perturbation, and you see this perturbation is enough that you get a traffic breakdown. That means traffic flow is also hysteretic. An additional perturbation is enough that you can get a traffic breakdown where none without this perturbation. Now we come to more realistic scenarios, showing what are the three ingredients of a traffic jam. First, we need high traffic flow. Then we need a bottleneck. Here the bottleneck is just the on-ramp emerging situation. That means more vehicles come here. And thirdly, you need an inconservative maneuver of one vehicle. And then a traffic breakdown and a traffic wave has emerged. And the perturbing thing is that you see the effect before the cause. So let's just look at, just mark a vehicle standing here. This vehicle now will accelerate, and then it gets into the next jam. And this driver thinks, oh my gosh, why do I need to stop? Why do the vehicles just not move on? Now the next wave is appearing, and this driver, because the waves are traveling backwards, sees the effect before the cause, which is counterintuitive. Now the next wave, and now the driver finally sees what is the cause, the merging region of the on-ramp. And once he leaves the on-ramp, now he's cut in by some other vehicles, but now he can move on. So that's the main effect. But also here I can, of course, when I increase the responsiveness, first I increase the outflow. You see here 3,000 instead of 1,000 before. And then I also eliminate the traffic waves, not the jam altogether, but at least it's homogeneously flowing. Interestingly, also an off-ramp, which seems a sort of anti-bottleneck, can lead to a traffic jam just by the perturbations. Because the vehicles, much vehicles want to leave this, you get some perturbations, and there's a spillover of the leaving vehicles. Eventually, you get a perturbation, although it's basically an anti-bottleneck. Vehicles want to leave. Notice that you cannot model this with microscopic models. I will never get a chance with microscopic models because this lane changing perturbation can only be modeled microscopically. Now your seminar is also about control. So I now want to show what speed limits can do. How do you model speed limits? Just reduce the desired speed of the speed limit. Of course, if you are a truck, the speed limit is always the maximum of the signalized speed limit and the 80 kilometers per hour. However, you see, here's a roadworks. You see that everybody managed to go to the 2 lanes in time to avoid jams. Now I change this speed limits to free traffic. Cars are no faster than cars. And sooner or later, some car will not manage to change in time in the lane. And you see what happens, traffic breakdown. It means slower is faster. And now even if you reimpose the speed limit 80, nothing can be done. So as the Germans say, the kid has fallen into the barrel. It's just a jam. You can try to make drivers more responsive. That will increase the outflow a little bit, but probably will not help. So that means, in fact, lesser is more. Now I will show another traffic regulation that is truck overtake ban on uphill. So here we have an uphill section, and the trucks are getting very slow because they are loaded. And here the uphill is ended and the trucks accelerate. However, the trucks are required to stay on the right lane, so no traffic jam will appear. Now I lift this overtaking ban. Now the trucks can also be on the left-hand side, and you see what happens. The trucks will break down also the cars, and traffic breakdown happens, and you get a real traffic jam, which even gets heavier upstream of the uphill section because of this perturbation. And here I think it's can be solved after some time if you enforce the traffic overtaking ban. Now you see how things are getting improved again. Another thing is in roundabouts. I don't know how the roundabouts in Korea are. Or we have left-hand traffic, here we have right-hand traffic. And in the roundabout, the ring traffic has always right of way. So it's if however you have the arms have priority, that means right before left, then you will sooner get a complete gridlock. Because if arms have priority, people wanting to go straight or left will sooner or later will be stuck. So now the ring is nearly completely full. It only I will increase the time lapse a little bit. Basically now we have a gridlock. And let's hope that if I lift, give the ring priority, maybe I can, yes, I think after some time you get the gridlock resolved. So we see with traffic simulations, you can show that you really need to give the ring the priority in the roundabouts. So now 2 last simulations, which I say in a sort of play, in a routing game. So basically first, this is the, let's first redo the time lapse. So this is the main road where some road work. And if you, let's first start the simulation with 0 deviation use. If you have 0 deviation use, then after some time, you get breakdown on the main road because the inflow is too much for the bottleneck. Now let's use much of a deviation and restart the simulation. Same inflow. Now you will probably see that no breakdown on the main road, but a big breakdown on the secondary road. So this is also not good. So obviously you need something in between. And that's where you can, where we have, I've made up a ramp metering, the routing game. In the routing game, if I start, I can just use this slider and then can slide it. I can, for example, say routing master, print say okay, and then I can just use some deviation, maybe a little bit at the beginning, and trying that I get as little congestion as possible. Now I've already lost, I've produced, no, I'm still good. So you can just, depending on the inflow, you can just vary the amount which is on the, which is deviated. And finally, I got a time, 224, which is not so bad. So you can try to get better than this, my deviation control. So there's another play, the ramp metering game. So what does ramp metering mean? Ramp metering mean I can set a traffic light. So these are all interactively. You can set a traffic light, for example, here. You can control it. So you can choose your weapons. You can also, if you want, to set some speed limits. Maybe I also set a speed limit funnel on the main road. So now I've imposed a speed limit downwards of this line and maybe a speed limit of 60 here. I can also change the signs. I can, for example, say this is 100 and this is 6, this is 80. Let's if I change it here, 80. Okay, so that's let's call the speed funnel in Germany in order to get reduce the speed and the same speed for trucks and car intersections. Now I play this ramp metering game again with some start, and if I play okay, then I can control the traffic light. It's best to leave only one at a time in order to avoid congestions on the main road. So only one at a time. So now I leave everybody because now I have sensed a gap. And now before the rest comes, I stop again. And now I leave just. And again, if I just I need to wait until the end, and then I get some time. And that can be, for example, also you can show if your car faster than 300 seconds. Okay, let's go back to this. So I'm now finished with my lecture, and maybe you have some questions.
Hello, can you hear me?
Yeah. I can hear you, yes.
Yeah. So thank you very much for your very interesting lecture and simulation. So on the chat, there are plenty of questions of the audience. So we will go through each of them. So yeah, there are many questions. So yeah, the first questions I want to ask you is that what is the meaning or the interpretation of the ODE in intelligent driving models? I feel that is a power 4 is hard to interpret physically. Yeah.
The interpretation of the equation of IDM, you mean?
Mm-hmm. Yeah.
Okay, let's. Oh, this is further below. I think here's it. No, here's it. Okay, so this is the first. The meaning of the IDM is basically you have one self-driving force. Let's first leave out this red term. Only consider this free term. Obviously, this is valid if the gap to the leader is very large, because then because it's squared and in the denominator, the interacting term will be 0. So what does the green term means? Let's first, yes? Okay, let's first assume that the initial speed is 0. Then we have just dv dt equals a. That means I will accelerate with the acceleration given by the model parameter a, for example, 1.5 meters per second squared. And I also will see if I resume speed at the initial, the acceleration will nearly keep the same. Because, for example, if I have half the desired speed, then I've just 1 minus 1/2 to the power of 4. It means 1 minus 1 over 16, which is about 94% of the maximum deceleration. It means only if going near the desired speed, my acceleration reduces. And it reduces smoothly, not just as a bang-bang control that I have an acceleration of a until I have desired speed, and then suddenly I go to 0.
Yeah, I know about
so that's the reason of this exponent or this to this 4. That of course you can some have it as a model parameter, but I play with it, and I think to a power of 4 is the best. So if I have to a power of 1, then I would have just a speed relaxation, which is also used in the optimal velocity model. But this will give unplausible fundamental diagrams, and it's also not plausible in reality.
So I see. Yeah.
Yes.
So, yeah, basically you can change the power of 4 function by any fast decreasing functions. Yes,
by any, you can change it by any exponent between 1 and basically infinity. If you have infinity, then you have this bang-bang control.
Yeah, I see. It's v is either 0 or v0.
Yes.
V substitute. Yeah, I see. So okay, thank you. Yeah.
Okay.
So the second question is that we can we apply these car following models in building self-driving car? Yeah.
Basically you can, because in fact with IDM, as I told, it has no reaction time, and self-driving cars have a little bit reaction time because the sensors need to be evaluated, and then the actuation, the brakings need about 100 milliseconds. And if you have an electrical car, the acceleration also takes maybe 50 to 100 milliseconds. If you have a internal combustion car, the acceleration even has a latency of 300 milliseconds. So there is some time, but it's minor compared to the human reaction time. And if you introduce this, you will see hardly any difference. So yes, you can. The IDM is basically an adaptive cruise control implementation. And in fact, with a modification of the IDM, I have already been driven in a physical test car on real traffic and on Volkswagen test tracks.
Yes.
And of course, there are some deficiency. One is, as I've already mentioned, that the time gap parameter does not mean the real time gap, but is a little bit higher. So this can be resolved by taking the IDM plus, which basically has a minimum function of the green term and minimum of 1 minus the red term. That just separates the free and the interacting regime with an continuous but not kink-free transition. That means you have a jerk at the transition. Another problem is if you get cut in by some other cars, then the IDM, by means of a square in the denominator, reacts too panicky. It means the initial braking deceleration as a response of this cut in is too strong. For this, I've developed a dedicated ACC model, but it's basically an IDM variant. So 𝐂𝐎𝐶𝐓𝐀𝐂𝐓𝐒 with a grain of salt, you can say this IDM is basis of following a module of an autonomous vehicle.
Yeah, thank you. So, yeah, I see. Yeah. So I see that is, thank you for your response. So yeah, the next my next question is that the car following model, yeah, it's by the name. It's only apply for car, right? So yeah, in Vietnam, yeah, there is people mainly use motorbike. So can car following model be adapted to this kind of traffic? Yeah.
That can be adapted, and it even is on this slide. I have bicycles to the right, and of course you can also use motorcycles or auto scooters. I can also show some simulation of mixed traffic flow. I will go back to the simulation side, and then we'll first get to my homepage. So this is my homepage, and there you can all the simulations. And there's also interactive mixed traffic simulation. The first, this is even lane-free, and here I have motorcycles, cars, and trucks. And in a lane-free environment, that means, do we have in Vietnam also lane-free the traffic, or is the most traffic now lane-based?
Actually, in Vietnam, there are more motorbike than car.
I can also I can increase the bike percentage. I just get the bike percentage higher. So a target bike percentage, of course, this only relates to the inflow. Maybe I even take the truck percentage a bit lower, and bike percentage even higher. Of course, it's only the new. Now we have many motorbikes. Obviously, there's some motorbikes because of the high speed, and you see how they squeeze through the bigger vehicles. So sometimes, so here you see they're even self-organized in a sort of group of smaller bikes just going. And this, of course, can also be used in a lane-based setting. For example, I can say I just make the with more homogeneous, and then I introduce lane. There's a floor field. There's a floor field here.
Yeah.
And then I have maybe I just increase the number of lanes just by decreasing the road width.
Yeah.
Now we have, for example, a 3-lane road, and now you see many motorcycles, and here they are even so if they want to overtake, they even will sometimes use the middle lane before. No, here not, but you can set it that in some counties motorcycles do not use lanes at all, but they just squeeze. But here you see that they can just overtake the cars and bikes on either side. So is this traffic which is more Vietnam-like?
Yeah. It's really, quite simple, quite similar.
Yeah.
Right?
So and so this is also, it can be also done interactively on my website. I just opened my website, so it's just mixed traffic, and this all can be accessed from my homepage, where there's this mixed traffic simulation, and here's this interactive simulation. You see that at version 13 and at version 5, so there's a much development. In fact, the simulators are the most called parts of my website. and even called more than many other websites of total shares.
Yes. So yeah, thank you for your very clear illustration. So I saw that you have source code on GitHub. So
Yes, yes, you
can
can get all the sources of the simulator on GitHub. You can
yeah,
download the whole thing, and then you can also run it locally.
yeah, thank you, thank you. So so the speaker have plenty of questions for you. So we'll start with some let me see. So what? So yeah, an audience has have asked you that when you start modeling a new traffic phenomenon from scratch, what is your typical approach? Do you begin with real-world data and fit the model, or you start from theoretical assumptions and validate afterward? Do you have any advice for students for approaching this field?
In fact, when developing this model, I started from theoretical assumptions and also from experience how I model traffic flow. And also I look at past models of that time. And there I realized that apart from the Gibbs model, there was no model on the market which includes the real kinematics. So all the past models failed when approaching a standing queue or red traffic light because they do not have this square dependence on their own speed, which is here coded in the desired gap. So basically, I started with the considerations leading to my safe deceleration.
Yeah, thank you. So
basically with this, I started with this derivation, and once this was finished, only then I added the remaining terms such that the model is complete. So basically, I first developed my what I would say unique selling point, which brought me I think about 6,000 citations alone, and then I developed the rest of it. And of course, I developed the rest that I have intuitive model parameters, which I can then adapt to all sorts of traffic data. Particularly, I've calibrated this model to a lot of trajectory data. We even have an own set of trajectory data, the Milano data set, which and there are also many other trajectory sets now available. And basically, this model calibrates well to all the sets. In fact, in many, there are also some benchmark tests, different models to calibration, and in most of these benchmarks, IDM or the variant of it calibrates best. And it's not much better than many others because there's I would say a glass roof for which is defined by inter-driver variation. But I think this IDM approaches this glass roof the most, which is possible for such a simple model with just 5 parameters.
yeah, thank you. So yeah, so well, so now is the time for anyone who can turn on your mics and ask a question to Professor Martin Treiber. Anyone has any audience has questions, so just open your mic. Or you want to raise your hand first? Yeah. So yeah, let's cool. Anyone has some questions for Professor? Yeah. Trang, please. Do you have any questions?
Hello, Professor. I have a question for you.
Yeah.
For high school students new to traffic modeling, do you mind if I have why do we need such detailed psychological factor like reaction time and risk attitude instead of just using IDM?
So, Minh, so first, this model has no reaction time or IDM, so it's more suited, in fact, to adaptive cruise control and longitudinal component of an autonomous vehicle. However, for real human drivers, reaction time has a big influence because I don't know if you're aware of general control theory, feedback control theory. Maybe you can even get it if you shower and you set your temperature. However, if you set the temperature by turning a knob, it will take some time until the shower has the desired temperature. And maybe you have turned too much. First, the shower is too cold, then too warm, then too cold away, and so on. And generally, this is a general phenomenon. If you have any feedback control loop, which you have here, because you have a control and the result of a control changes your input variables for a new control. So any reaction time, any delay will lead to oscillations, just as in this shower examples. So it's hugely important for modeling human drivers to also include reaction times. So that means leading to a delay differential equations system. However, as I have showed in a paper, if you compensate this reaction time for a temporal speed adaptation, and optional also by multi-anticipation, you basically compensate this response time, and the net effect is the plain IDM behaves similar than the extended model with reaction time and temporal anticipation. So in this sense, so with a grain of salt, you can say the IDM also can be used for modeling human drivers. But of course, if you want to do psychological experiments or measure the influence of reaction times, you need to have the real thing.
Yeah. No, sure. Okay. Yeah. Yeah.
Hello. Hi, can I just ask a question? So, is it noisy here? Can you hear me clearly?
Sorry.
I cannot really not really hear your question.
Yeah. Can you repeat that?
Yes, repeat it. Yes.
Yeah. So anyone who asks the question, please repeat it so the speaker can hear it. Yeah. Phúc, you have questions?
Hi, Professor. For high school students new to traffic modeling, do you mind if I ask why do we need such detailed psychological factors like reaction time and risk attitude instead of just using ITM? And also, where are these factors originally inspired from?
The first question with the reaction time, I think I've already answered. Basically, you can compensate for reaction time by speed anticipation, what drivers do. So for practical simulation or operational reasons, you can just use the plain IDM because it has no temporal anticipation, but it has also no reaction time, and these two effects basically compensate each other.
Yeah. So yeah, I have. Anyone has questions? Yeah. Someone is talking. Hello. Yeah. So we. Yeah. I have another questions. Yeah. Is that when you use this model to to support some policy makers. So how can you show that your simulation is indeed accurate and and it's and it's very fit to the reality? So yeah.
Of course, this is 2 points. First, if I simulate counter realistic situations, for example, implementing new speed limits or new traffic lights, then of course I cannot demonstrate that the simulation gets right. However, in the preliminary setting, I can just try to reproduce observed congestion spiral trajectory data and also observed macroscopic outcome. That means the right flow density diagram, the right outflow from a jam, and the right accelerations and so on. And also whether stop and go traffic appears or not. So that's called calibration. And once I've calibrated the model on some data, there needs to be a step called validation. It means apply the calibrated model to new data, which are known, but which the model does not know. And if a model with the calibrated parameters also can reproduce the new data sufficiently well, you can say that the model is validated, and then you can let it loose to real applications. But of course, if you simulate some counterfactual things, there's no definitive proof.
Yeah, I see. So there's how to prove that your simulation fit to the real scenario. So yeah, thank you. It's but when you talk to some kind of policymaker, assume we have some role of consulting to them for how the traffic policies should be made.
Yes.
So what should we tell them from the model? Yeah. How should
that's difficult, because probably this policymaker will know nothing about simulations. You can, for example, try to visualize some traffic data, then you can visualize what my model does or your model does with the data, show that this is similar, and then you can show some, I think these dynamic simulations, which I have on my website, should also convince some policymakers. But of course, in order to convince them that the model is sufficiently accurate, you can only refer to its ability to reproduce past data.
Yeah, thank you. Yeah, thanks. So, well, yeah, there is time for another questions from the audience. Anyone who can turn on the mic and ask Professor here some questions. So time for some last questions. So yeah, Zapin, do you have any questions?
Hi, Professor. I have 2 questions regarding the slide plausibility to steady state relation.
Yes? I think it was no, further up. I think this depends on the speech. Yes, here's a steady state, yes.
Yeah.
So this is your slide with the steady state, yes.
Yes, this question is, I assume the steady state equation and the varieties in the slide are currently built up on a deterministic system. In reality, human reaction delays and distant estimation error can be modest using random variable. How can we incorporate the noise factors? I was wondering if we introduce them through a stochastic difference equation, would the stability of the equilibrium velocity function and the divariate limits be affected?
That's what I had at the beginning. So there are different ways you can introduce noise. First, you can just have acceleration noise. That means you just add to your acceleration function f, which is deterministic, you add some, in the simplest case, just white noise. And if the situation is string stable, then this white noise will just lead to some fluctuations, but not changing much the steady state. If, however, we have a string unstable situation, then the noise can lead to traffic waves, which are by definition not a steady state. So you can define a stochastic steady state, which just means the distribution functions and correlation functions do not change in time. That's basically a generalized steady state. And that you can do with, for example, acceleration noise. And the result is that basically the means of the steady state distribution functions will essentially lead to the same steady state relation.
Yes, thank you. I can understand this. Yeah.
So yeah. All right. So thank you for your very interesting Q&A sessions. So even though I know the audience still have plenty of questions for us, our time is unfortunately running short. So I'm afraid we have to wrap up the Q&A session here. So I must say, I am incredibly impressed by how active and enthusiastic you all have been tonight, this afternoon, judging by the sheer volume of the questions submitted. I truly hope this session has answered what you were looking for. If you have any lingering questions, please feel free to send them directly to the Hanoi Mathematical Modeling fan page. Our team will gather them, consult our speakers, and we'll get back to you as soon as possible. So yeah, just a quick reminder that there's a registration link and the round one prompts for the 2026 Mathematical Modeling Competition, Entropy, are officially live on our website and fan pages. This year's challenge promised to sharpen our mathematical modeling skills while expanding your knowledge in the field of traffic and transportation. And what brings us to the end of this afternoon presentation, the insight was shared by Professor Martin Treiber have certainly give our students a fresh, specialized perspective on the power of mathematical modeling in transportation. So on behalf of the organizing committee, I would like to extend our heartfelt thanks to our partners and especially to our incredibly passionate speaker, Professor Martin Treiber.
Thank you.
I also want to thank all of you, our wonderful audience, for spending our afternoon with Hanoi Mathematical Modeling to explore and learning new things. Last but not least, I will wish you all have a highly productive week ahead. See you all in the upcoming stage of the 2026 Mathematical Modeling Competition, Entropy. Thank you for attending the webinar today. Yeah. Thank you and goodbye.
Yeah, bye.
Yeah, thank you so much, Professor Martin Treiber.
Okay, so I will leave now. Yeah, many thanks for your letting me speak. Yes. Okay, see you.
Yes, thank you. Thank you so much for presentation. Yeah. So for the audience, you can leave now. Thank you for your for your attentions. Yeah. Thank you so much. Ý kiến này chưa?